So, we're talking about these tables for drag coefficients, and I need you to read the one in your text and see. One thing I need to call to your attention is these are the drag coefficients for high Reynolds number. It's saying Reynolds number at 10 to the 4 or greater than 10 to the 4. That's turbulence. These, unless specified, right? See here they're telling you this one's for laminar or turbulent. These are for laminar or turbulent. So there are some that will specify whether you're dealing with laminar flow or turbulent flow. But for the most part, these numbers are for turbulent flow conditions. And then on the next page here, you see they've got, on our text, they've got kind of some standard shapes, some cars, some vans, parachute, tree, a wall, sphere, some other kind of normal shapes. But again, up here at the very top, it's going to tell you these are for a Reynolds number of 10 to the 4. What is that, 10,000? It's a 1 with 4 zeros? Yeah, it's a very high Reynolds numbers, very turbulent flow, unless otherwise specified. So just make sure, and that's, guys, that's, you guys are juniors in engineering at this point. That is, you're reaching the point where anytime you pull an equation, and some of you guys have gotten in trouble on this on the homework. Anytime you pull an equation and try to use it on a homework problem, you got to make sure that equation actually works for the homework problem. Just because the internet told you to use this doesn't mean it's correct. Only use things that make sense. Well, and that table is telling you that unless it's otherwise specified, those numbers are for turbulent flow. So don't use them for laminar flow, or don't use them period unless you know you've got a very high Reynolds number, meaning you probably need to find your Reynolds number before you try to apply one of those. And let's do that. We've got an example here. Right? Got an example. Alright, so we've got air, 1 atmosphere, 60 degrees Fahrenheit, flows at a rate of 100 feet per second. That's fast, right? Goodness, I think about 80 or 90 feet per second, almost 90 feet per second is 60 miles an hour. Right, so that's where upwards of 70 miles an hour, so that's really fast wind. They're saying we've got a 10 foot by 10 foot square sign placed on top of a 60-foot rod. I don't know if that makes any sense. With a diameter of 12 inches. That seems dangerous, but that's what they're saying. They want to know the maximum moment applied to the rod. Again, I'm assuming you've had statics. If not, you're in the wrong place, but here we are. Alright, so let's see if we can draw this thing out here. This is not to scale. You guys have already seen my drawing ability. It's not great. Right. So we have this sign. Can't draw this as well as I can on a smartboard, but here we are. Alright. I'd love to write something funny on here, but I just don't think I drew it big enough. So, it should be square, even though I've not drawn it square. So this is 10 feet by 10 feet. And this is a 12-inch rod, again, not drawn to scale, or a 1-foot rod, if you will. And this is, again, not to scale, 60 feet above the ground. They want to know the maximum moment. Steve, we've not talked about moments in here. I know, but you talked about moments in statics. You've already had statics, so we're supposed to know that. Determine the maximum moment, not just a moment. Determine the maximum moment. Where does the maximum moment occur? Well, that's an interesting question. Where would the maximum moment occur? Right? The maximum moment within this rod. So, well, where would that occur? Well, the moment's going to be a function. And you just think about that like any other problem I try to teach you guys how to think about. What controls a moment? Well, moment is force times distance. Okay. Can we increase the force? No, the force is going to be caused by this drag force, and we don't have any control over that, and that's actually what the problem's asking us to find, is the drag force. So the only thing I can change is where that the length along this rod that we try to take the moment about. Well, if you get the furthest away from the forces, and so I'm going to have a force applied on the sign, I'm going to have a force applied on this rod, and the farthest point away from both, or at least away from the force on the sign, is going to be down here at the bottom. Right, so that's going to give me probably the highest moment is get as far away from this force as I can. That's going to give me the maximum moment. So I'm going to try to find the moment down here at the very bottom of the rod where it's sunk into the ground. Now, why is that important? Why does that help us? Well, in strength of materials, you're going to sometimes try to find this quantity called stress, which a lot of times we'll represent with sigma. Sigma is going to be found with my over I. Okay, some of you guys have already had strengths maybe, so maybe you already know this. The maximum moment, this is the moment. So this is moment times the distance. We call it the distance to the neutral axis divided by the moment of inertia, which is based on the shape of the object. So these two you're not going to be able to control. This is what you can control. This is your variable, the maximum moment. And so the higher the moment applied, the higher the stress, and all material can only withstand a certain amount of stress before it breaks. So basically what this problem is saying is, hey, look, we need to know whether this sign can actually withstand a roughly 70 mile per hour wind. How do we know that? Well, we need to know the maximum moment to go into the stress equation. And how do we find that? Well, that's a fluid mechanics problem, and that's what we're here doing. Right? So our contribution right now is the fluid mechanics problem. So let's talk about the fluid mechanics problem on this thing. Okay, so if we look at, give me the ink back. Right, if we look at this thing, realistically, right, you're going to have a distributed load applied here and a distributed load applied here. Okay? And so what we're going to do is we're going to turn that into, we're going to assume it's a normal distributed load, and we're going to apply that force. This is going to be the drag force on the sign, subscript S. And I'm going to have a drag force on the rod. And this is an S. I know it's a terrible S. I'm sorry. But so rather than work with these as distributed loads, we're going to turn them down to a single force. It's going to be located in the middle, right? So this drag force on the sign is going to be located in the middle of the sign. Drag force on the rod is going to be located in the middle of the rod. And we're going to use those distances and these forces to determine the moment, the total moment applied to the rod. So that's what we're going to do. So I'm going to set this aside, and hopefully these help a little bit. We'll work the rest of this then on paper. Okay. Yeah, we got enough time to get this started. So, givens. Okay, I've got air, 60 degrees Fahrenheit. That's important because it's going to tell me properties of that air. It's also at 1 atmosphere, so because it's a gas, I probably also need to have an idea about the pressure. It's going to flow at a rate, so I've got a speed here of 100 feet per second. Again, you go ahead and do the conversion. If you think in miles per hour, go ahead and do the conversion so you know roughly how fast that is. That's fast. I want to say it's on the order of 70 miles per hour. Okay. Now, the area of the sign, it's a 10-foot by 10-foot sign. So it's a 100 square foot sign. Square foot sign. Okay. The length of the rod, we said, is 60 foot. And the diameter of the rod is 12 inches, or if you like, 1 foot. And we want to, so again, I've got this sign. I've got this sign. So it's 10 foot by 10 foot. And this rod, 1 foot, 60 foot. Okay? We want to find the maximum moment applied to this thing, which we said the maximum moment is going to be the moment applied at the ground. Right? We'll call that point A. Moment at point A. Okay? All right. So how do we find moment? Well, we draw a free body diagram. It's pretty simple. I've already kind of roughly drawn it. Let's draw it on paper so it's a little better. Drag force applied to the sign. Drag force applied to the rod. Distance is here, so that's going to be applied in the middle of the rod. That's going to be 30 foot from point A. And I've got another 30 foot up to the top of the sign. And then another 5 foot to the middle of the sign where the drag force on the sign is being applied. So I have two forces being applied to this thing. And I need to determine the moment about point A. And that's what we want to try to find. So what is the total moment applied to point A? Or if you want to consider this thing to be static, because it's a fixed support down here, you've got AY, AX, and I've got my reactionary moment at point A, because it's a fixed support at point A. So this is a complete free body diagram you'd see in the statics class. So what we're trying to find is we're trying to find this reaction moment at A at this point. Okay, that's really what we're after. It's the reaction moment at point A. Okay. All right. So, well, to do that, as you can see, I need to find these drag forces. So the drag force on the sign is going to equal, and we said earlier, it's the lift force. We said the drag force right here. The drag force is 1/2 coefficient of drag for the sign times the density. This is going to be the density of the air times the speed squared times the area of the sign facing into the wind. And the drag force on the rod is going to be 1/2 the coefficient of drag for the rod times the density of the air, not the density of the rod, the density of the air, times the speed of the air squared, times the area of the rod facing into the air there. Okay, so far so good. So, all right. So again, standard practice, what are we looking for? We said we're looking for this. How do we find this? We need this. We'll do our sum of moments here in a second, but I need to know these forces. All right, here's these forces. What do I need to know now? Well, I need to know the density of the air. I know this. I know this. I can find this. Right, that's easy. The area facing into the rod, it's not the surface area of the cylinder. Right? Remember, the only thing that the air sees here flowing into this thing is just this width and the height. So the air is actually pushing, it doesn't matter whether it's pushing against a curved surface or a flat surface, the area that it's facing into, the projected area, is going to be the area of the rectangle, essentially, covered by that rod. So it's going to be 60 square foot. So the area of the sign is 100 square foot, the area of the rod, 60 square foot. I know the speed, I do need the densities, and we're going to talk about the drag coefficient. So, I need density of air in English. It seems like that's a nice place to stop. I'm going to go pull that up and come right back. So a little bit of a pop here.